Today's talk, Anatomy of a Request, Beyond Back-End Processing. You know, I was having a chat with Kelsey last night, actually, and he asked me about what the talk is going to be about, and I told him it's going to be about the journey of the request. And he said, this is funny because at Google, we used to give, when someone joins, the first thing we give them as a presentation is the journey of the packet, which is very similar to what we're going to discuss today. But when we look at the idea of a request, the first thing that comes to our mind is the processing of the request. That is, I'm making a request, and then I'm making an API call, an HTTP request, and that either goes to disk, reads some HTML file, JSON, retrieves that and sends back the response. Or you either go back to the database, do some queries, parse that results, make it either in a JSON response or protocol buffer and return it to the user. We always think of the processing aspect. Some API calls are more expensive, like I am actually doing a CPU-intensive operation, let's see, calculating the prime numbers, for example. So that's also a request. But a request is actually way more than that. And that's the topic of today. What is going on from the moment I write the request as a client until it's received on the backend? And there's the hops between. There's load balancers, there's API gateways. What is really a request? And that is the question that I am fascinated about, what a request really is. Because you see, a request, to me, the way I look at a request is, it's a message that has a start and an end. And that start and an end is defined by a specific protocol. Because you see, when I receive an HTTP request, the reason it's a request is because it's bounded by the HTTP protocol. The HTTP protocol spec has okay, this is how you started HTTP request, this is the verbs, and this is the length of that request. And you need to start somewhere, and you need to end somewhere. Why? Because without this boundary, you have no idea what are these packets. And that's another topic, because today, the only medium to send stuff on is the TCP. And the other medium is the UDP. TCP is just a streaming protocol. And I struggled with that concept before. It's like, what is a streaming protocol? A streaming protocol is just a bunch of bytes, and the only one guarantee is those bytes are in order. There is no end, and there is no beginning, there is no end to this stream. Well, technically there is a connection, of course, and there's the boundary of the connection. But there's just a bunch of bytes. So the job of the higher level protocols, which is HTTP, is to define the chunks of these bytes. Okay, I'm receiving these bunch of bytes, all right. Oh, I just saw a GET request. Let me start reading. And then until you reach the end of that request, you have one message. That is expensive, that takes time. And that I want to focus on that aspects of things in this particular case. So here are some examples, just few examples of requests. To the top left, we have a classic HTTP request. Well, HTTPS, because we have encryption on port 443. But we're sending a post request. The client, in this particular case, understands how to write HTTP request. Why? Because there is an HTTP library that has been baked into the client. Unfortunately, these days, everything is invisible for us. It seems like we're building on top of libraries and libraries and libraries, and things became so easy and simple on the outside, but we've hidden so much. And with this talk, I'm trying to kind of remove the curtain and see what's behind it. That's my job. I love this stuff. So there is a client, there is a HTTP client protocol. And you probably use the fetch library or Axios. That eventually calls that library. And that writes the request. And then the backend will have a corresponding HTTP server library that knows how to listen for requests and parses requests, right? And then also writes responses back. So the second type of example here, we have a Postgres server, and then we have a client which has a Postgres, you guessed it, protocol library. Without this protocol, we cannot do anything, right? It's like a language, if I'm speaking a language, if I'm speaking now Arabic, most of you won't understand me, right? But because I'm speaking English, both of you have this knowledge, this common protocol that we are speaking and we can understand, right? So Postgres in this particular case is listening on port 5432, and it understands the Postgres binary protocol. And as long as the client has the corresponding Postgres client request, it will send a select statement, select star, in that format, in that particular format, a request. And the Postgres server will understand how to read and parse this. And that will return the response. Same thing with SSH. SSH is built on TCP, just like Postgres, just like HTTPS. Well, you can also build HTTPS on top of Quick, but that's another topic. But most of this stuff is built on TCP. Right. SSH, the bottom left, is listening on port 22. And if I'm connecting, same thing. SSH is a protocol. So you need an SSH client library, and there is an SSH server side, which understands how to parse an SSH command. Well, we call it command, but technically, if you think about it, it's also a request. It has a start, has an end. And you get back a response. And technically, the response also has a start and an end, the way to parse it. But our focus here is on the backend and request. And backends accepts requests, right? The final example here I have is a DNS. DNS also a request. But this is the only differences here on top of UDP. So we have a DNS resolver listening on port 53, and you send a DNS transaction request on top of UDP. Same thing. It has to have a specific boundary. And the interesting thing about this request that you send, it can, no matter what the transport layer is, it can be fit in one packet or it can be on 10 packets. It doesn't matter. And that is the single most important thing to understand. That is, it's not one-to-one, it's one-to-many. And because of that, the backend must read and read and read and read and read until it discovers the end of the request. And that every read has a cost. And if you don't read fast enough, that has a cost as well. I'm going to talk about that as well. So let's zoom in into just the HTTP example here. So I have an HTTP client, and I have an HTTP server. The first thing we do, and I'm going to assume TCP for simplicity here, is to do a connection. We establish a medium by which it is trusted between the client and the server, and that medium will start sending stuff in it. And because we're using TCP, which is a streaming protocol, it's nothing but a bunch of bytes. Now, these bytes will be eventually encrypted. They might have HTTP. They might have any other things. It doesn't matter. But it's the fact that they're just bytes. And the job of this connection handshake or the protocol is to make sure the bytes are received in the order they are sent on. And that's both a good thing and a bad thing, because we're now forced into this order. Sending multiple requests becomes interesting. But let's just focus on the idea we're having a connection. On top of that, once we have the connection, we do usually a SYN and a SYNAC and an ACK, and then this is where the server and the client exchanges the window sizes and the sequences so that they can label the segment. Every segment is labeled so that we can ensure the sequence in which the order of the packets. And to label something, you need a starting segment, right? Sequence number. So these guys exchange those starting sequence numbers. So now we have a connection. On top of that, these days, we cannot do anything without encrypting because we live in a zero trust environment most of the time. So we need TLS, transport layer security. So this stage is, the goal of this is to exchange symmetric keys. Well, exchange secrets in order to create symmetric keys. And these symmetric keys should be only available to the client and the server, and then they will be used in order to encrypt anything that we send on top of this connection. In that particular case, we're talking about requests. So we're encrypting requests. So we're adding additional overhead. And we had a fantastic talk yesterday. William actually gave that talk about TLS, and because it's expensive to do the handshake, because it's expensive to do the connection handshake and the TLS handshake, we try as much as possible to resume an existing TLS handshake so we can not take the hit every time, because there is a cost, there is fixed cost to that. So if we can eliminate it, that would be great. But the third box is the actual request. We have a request, we're sending a post request, / headers, body, and then the whole thing is encrypted using the agreed upon symmetric key. And then we send it over, and then we receive the response. What I want to do here is zoom in a little bit even further. Let's talk about user and kernel space. TCP as a protocol, which is the connection handshake, where is going on, lives in the kernel. And the kernel is basically where the OS is, right? So it has intimate connection with the hardware. It's close relation to the hardware. So here at the left side, we have the client side, and where the right side, we have the server. At the left, we have the yellow box, which is the kernel of the client, and then we have the user space, which is the application. And guess what? This application, the HTTP, is an application. Your SSH library is an application. Your browser is an application. Even the TLS library is in user space most of the time. Right? So that understanding that where code runs is so critical, because there will be chatter going on. So what kind of chatter going on here? So the backend, the first thing here, when we create on the left-hand side, I'm going to create a connection. So we get this client connection socket, and we get a number assigned to it, file descriptor. Let's say it's 6. At the right-hand side, we have the server side, and we listen because we need to listen on a specific port and address. In this part of the case, I'm listening on our addresses. Mostly bad idea when you do that. And essentially, when you listen on a specific port, you get also a file descriptor. That's a socket. We still don't have a connection yet, right? So what we're going to do is the backend, after that connection has been created or the handshake has been done, what happens is the kernel left that connection in its what we call the accept queue. It lives in the kernel. And the connection is not yet created. To create it, the user space, the app, our backend, must call a function call or a system call called accept and give it the listener socket in order to create a connection. You see that? So there is also some work here to even create the connection. Now I want you to scale this into millions of clients connecting. You have a bottleneck here. You have if you have a single socket, everyone is competing to accept connections. You have mutexes, you have all sorts of delays. We can talk about that later, how to solve that. But all these problems mostly are solved, and it's already in HAProxy. But accept. Once you hit accept, now you have an actual corresponding connection file descriptor, which in this case 8, that corresponds to the client. Now we can start reading and writing. Reading and writing what? Bytes. There are no requests at this level. There are no encryption, there is nothing, it's just bytes. So keep that in mind. So the first thing that we're on the client side, we want to write the request. We have this request, it's called post, a bunch of headers, and we have a body, and there is an end, right? And I want to write it. But before we write it, we have to encrypt it because we are in an encryption session. And we have this key that I have already negotiated, and now I'm going to encrypt that. In order to encrypt, if you think about it, how to encrypt things, if I have this chunk of data, so usually fixed size block, you need technically to copy in order to encrypt. You cannot encrypt in place, right? Because in case of corruption, you cannot go back, right? So copying also has a cost. And we'll talk about this in a minute, but every copy you do, not every, most copy, memory copy, goes through the CPU, because that's how it works. If I want to copy a certain chunk of memory from this location to this location, you need to read it all the way to the CPU. You need to write it through the L3 and L2 and L1 cache and the registers. And then when it gets to the register, there's an instruction called, okay, store, because load, and now store it. Where do you want to store it? In this location. So you got to write it back. So every copy, most copies, because DMA is an exception, but most copies goes through the CPU. And that's why memory copies cost CPU, which is kind of a little bit odd to think about, but they do. So here we have consumed some CPU and consumed some CPU for the encryption itself, of course, because TLS's algorithm is all encryption, right? And CPU intensive. Now we have that. The next step is one of the most interesting things. Now, where does this data live? Where does this data live? It lives in the user space, right? It lives in the app. It's in the virtual memory space of the process. To write to the connection in order to send it to the network, now because we're ready to send it to the network because it's encrypted. But to write it, we have to write it to the kernel. Right? Because we write and we specify the file descriptor of the connection, which is in this case 6. That's my connection. I want to write this to the connection. And this, because the kernel batches, it's expensive to trust the client. Right? If anything the client sends, I immediately send it to the network, I'll end up sending 1 byte to the network, which is that's a lot of overhead. And there's a whole algorithm that controls this called Nigel's algorithm. Because how long should I wait? It's a very interesting question. That's why I love this stuff, because you can dive deep into any of this stuff and write papers about it. Right? If you write, here notice I wrote something, so that's a copy, so CPU, but it's copying from user space to kernel space. So I'm copying, so I'm using the CPU, but I didn't send it to the network yet. The third one, I decided, well, we have enough data. Let's ship this to the network. And it's usually, you try as much as possible to fill 1 MTU, maximum transmission unit. Right? Just like as much as possible. Like this is the segment of the TCP. I want to send this as much as possible. So we sent it over. And it goes from the kernel all the way to the network. And this is where the whole IP takes over, data link, and then goes to the physical network, which is in case of fiber, it's light. In case of Wi-Fi, it's radio. In case of Ethernet, it's electric. And then regardless, it will be transformed back all the way to the second server, to the server side. Now we have the encrypted byte where in the kernels of the server or the backend, not the user. The user have no idea about it. Okay, and then we've written the whole thing. This is just an example of writing the whole other rest of the packet, and we received all of them at the backend. Now they are encrypted chunks in the kernel. They are useless at this point. So now the backend responsibility is to call read. You might say, I never call this read. What is this read? It's all, again, back to the libraries. Every library you use eventually must call this system call, because otherwise you will never get your data, right? So to be more specific here, that data lives in what we call the receive buffer of the kernel, of that TCP connection. Every connection you create will have two things, send buffer and receive buffer. And in this particular case, all this data lives in the receive buffer, and the kernel will keep it there until the client, in this case the client is the backend, will call read and will purge it from the receive buffer and will copy it to the application. So now we're calling read again on read 8, on the connection that we created, right, on the server side. And then we copy it. That's another CPU. Copy, copy. We're copying it. And then we keep copying until we have the entire encrypted chunks in the user space. Sweet. That's not enough though. These are just bytes that are encrypted. I cannot tell what this is. So I need to execute OpenSSL or WolfSSL library, which lives in the user space, which is another, set of instruction that will take these encrypted bytes and decrypt them, which I may do a couple of copies in the process and use the CPU more. And you can see how much the CPU is taxed, right? And we didn't even get to the request to processing. Forget about that, right? We didn't even reach that. We're still trying to look at the request. So now we have a bunch of decrypted chunks. What is the request? We still don't know. Where is the beginning of the request? Where is the end? We have no idea. We have to do the next thing, which is parsing for that request. So now, the backend protocol, back to the protocol library, kicks in here and start just, parses like, okay, what do I have here? Oh, I have post. Okay, post is good. Okay, that's the start of the HTTP request. I know that. I have an HTTP library here, so I know how to parse this stuff. If it's HTTP2, I need to use HTTP2 parser, and so on. So now I have all of this stuff. I parsed all of this stuff, and now I have a full request object. And if you ever reach that stage, that is when, specifically in Node.js, there is an onRequest event. That is when that event will fire, that point. Because now we have a false object. And in this particular case, to learn how we parse this, we looked at the header and said, all right, there's a content length, and the length is X, so we have to move X number of bytes until we read the entire thing, right? That's one way to read HTTP requests, right? Define the boundary of HTTP requests. Okay. And here's one thing. We might have not read enough bytes to get a full request worth, right? Because we're reading bytes. We have no idea. We're reading just encrypted bytes of all things, right? So we have to encrypt, we have to read and decrypt, read and decrypt. And maybe we got I wish I had a laser, but maybe we had halfway through. We have halfway through the headers. So we need, that's not a full request. Let me read more. And so that cycle keeps going until we have a full request object. And that request object then gets sent to whoever handler, and then we'll go through we're not ready to execute yet, by the way. Not yet. So now, there's another step. This is optional, but I thought I'd add it. Decoding. Most requests have this idea of compression, right? And compression is we don't have header compression anymore, request header compression, because we removed that because of an attack called crime. I forgot what it stands for, CRIME. But essentially, it's because someone can sniff and detect what is inside a packet based on how big the compression is. So they will send something and it will see how far the compression gone. So we stopped compressing headers because of that reason, most of the time, right? I have to mention that this is HTTP 1.1. HTTP 2, we have another completely different algorithm for compression, which is HPAC, which doesn't use it uses like a map table, not really an actual compression. Okay, so but compression, body can be compressed, right? And body can be specifically encoded, right? Like JSON is an actual format. Protocol buffer is an actual format that, if you think about it, is also a protocol by itself, right? You need to understand how to parse it. JSON, you need to understand how to parse JSON. And you might be familiar with some. I had a case where there was like a C++ library that was really bad at parsing JSON. And by switching it to another library, I got like 90% performance. And that's this, decoding the body, right? Because if you have large body, more work needs to be done to decode. And we get a JSON object, so this is another step, and we might go through this. And then finally, now we have a ready object request with an actual JSON object that we can read, right, and parse and understand. And then we can process this. I can now, the world is your oyster. What do you want to do here? You want to use the same process to execute this? You want to spin up another thread and delegate this request to? You can do that. You can have an existing thread pool and just throw this request on it. You can do anything. And then, of course, once you have the response back, you compile it, and then you write it back. Of course, you cannot send it plain text. Remember, this is an encrypted channel. So you have to encrypt it, do a copy, right? And then write it back to the kernel. You never write to the network as a user, right? You write to the kernel, and the kernel will decide when it feels like it to send it to the actual network. Yeah? And I think there is a command to flush, to force. It's like, I know what I'm doing, kernel, go and send it. But I don't know if that is even trusted. So yeah, that's the journey of the request here. We have it. So accept. So I gotta say that the accept part and the encryption part happened once, at least the connection establishment, that accept. You only accept the connection once, at least you hope so, right? You don't want to create a connection for every request, right? You send and you close it. We used to do that in HTTP 1.0. We stopped doing that, right? We want to keep the connection alive and then send as many requests as possible. So then you read and you decrypt, and then you parse, and you read and you decrypt and you parse, and you read and you decrypt and you parse, and then you then decode optionally, you process, and you're done. That's the journey of the request. And I skipped so much other stuff here. I wanted to go through more details about the kernel itself and the data structures, but we're gonna run out of time here. We have 10 more minutes. I'm gonna talk about some considerations here. This is my idea of going a little bit in depth. So the first step, accept. How fast the backend can accept connections. Because I want you to think about that, right? As you're receiving tons of these sends and ACK, those connections will be, established by the kernel. You don't have to do anything. But then the kernel will add that, the connection parameters, the source IP and the source port, in what they call the accept queue, and it will be added. So another connection will come, will be added there. It's not ready to be, it's not a connection yet. It's just ready to be accepted by the backend, right? And you can control how large the accept queue is by specifying the listen parameter. And when you call listen, you say specify how large is the backend here, the backlog. And then, of course, you can control that large, but you can have something called socket sharding with the option, the socket option reuse port, where you can have multiple processes listening on the same port, so each one will get its own accept queue, and each one will call accept on their own queue, and the kernel will distribute the connections on these queues, as opposed to having many processes fighting on one listener socket, trying to accept from the same queue, because, you know, right, if you have one thing, you always have to have mutexes to protect it, right? So we have, there's some docs here I have for the kernel setting optimization. Read, how fast the backend can read data, that's also interesting, right? Because if you don't read fast enough, because let's say you use the same process to execute, then you don't have stamina, if you will, to actually read, right? Because your process is busy doing something else. Then if you don't read, the receive queue will pile up. And if you pile up, the kernel will say, wait a minute, this process is not reading stuff, so I better tell the client to slow down. So the window, the flow control window will shrink, and the client will slow down. So that will all happen naturally without you even knowing, just because you didn't read fast enough. Running out of time, so going through that. Of course, TLS, we have HAProxy evaluating a bunch of SSL libraries, because each one has a cost. Because we've seen just the basics of SSL. So you need to do this right to make it as fast as possible. So there's a lot of room for improvement here. Of course, parsing, we talked about that a little bit. H1 consumes less CPU than H2 and H3 because they have a different binary in binary protocol. And then we have decoding the body. Yeah, we talked about that, decompressing. Processing, yeah, you can execute delegate to a thread. This is one of the best blogs I ever read back in 2021 from Willy. And this kind of inspired me to start all this journey about the backend and all this stuff, right? Is how HAProxy forwards over 2 million HTTP requests per second, you know? And I was like, how is that even possible? Because 2 million is a large number, right, per second. And I wanted to dive deep into that. So it's a fantastic read. I think there is a new version they're working on. There's, of course, this very recent blog post about the state of SSL stack. Because we talked about how SSL, like there is encryption and you decrypt, and there's the handshake, and you need to do session resumption, and how much. They did a comparison of all the SSL stacks, and so it's a fantastic read if you want to go there. This is a very fantastic tweet from Willy. It's a reply to, I think I tweeted, why modern software feels slower. And what I said is like, the idea is because we keep developing on high-end machines, we mask bugs, we mask memory leaks. All of this stuff is hidden because we don't see it. All machines are great, you know? I have 16 gigabytes of RAM, I have all this, cores, I don't feel it. So what they do in HAProxy is actually, I didn't know that. They make sure the test pass on a 500 megahertz, 256 megabyte of RAM, which is amazing. It's challenging. I'm pretty sure it's painful too. So here's some configurations that I'd like to go through. So the first one is net.ipv4.tcp-rmem, which stands for the receive buffer. We talked about receive buffer, right? That's this. When you establish a connection, you get a receive buffer for free and a send buffer. Send buffer where the data you're sending, receive buffer is where your data you're receiving. So you can control how big is this for the kernel by this configuration. By default, you get, I think, 128 kilobytes. which can be tiny. So like HAProxy recommends changing that because HAProxy is like in the way, right? And this is another thing I didn't mention, right? Whatever we discussed, the journey of the request, the anatomy of the request, imagine now doing this for the CDN, which is a reverse proxy, right? Then you have the load balancer. Then you have the API gateway. Then you have the actual backend. That, what we just discussed, decrypt, encrypt, decrypt, encrypt, is happening all over again. All over. Happening in the CDN. It's happening in the HAProxy, the load balancer side. It's happening on the API gateway, because that's just another reverse proxy. It's happening also at the backend. So it's like, the way I think about it is like a car and slowing down as you put more obstacles on top of it, you know? And so the request is very fast. The throughput of the request is very fast if it has less friction as possible. So yeah, so you can control the receive buffer. You can control the send buffer with this option, TCP WMEM. I have no idea why it's W. There's the letter W is not anywhere in the send buffer size, so I don't know why. Why is it not SM? Max, SO max connection. So that controls what's the maximum number of connection that can be left in the accept queue, right? Remember when we establish a connection, it goes to the accept queue, and then when the backend calls accept, it pops from that queue and goes to the application, and then it's gone from there, right? So if you have a slow application that doesn't accept fast enough, then you will have essentially a problem, right? You have that. You will have, you won't have, clients will get an error connecting when this gets filled up. So you need to increase that a little bit. Hey, we're done. That's all the end. I'm gonna leave it for if you have any questions and answers. Thank you so much. Appreciate you guys. I think I went a little bit over.
Awesome, really enjoyed that, Hussein. So we do have, again, microphone runners. Raise your hand. We have Zach over here, somewhere else. So if anybody has a question, we have one right in here, and you can put them in the stream as well. The team will give them to me here on the iPad.
And I'll repeat the questions.
I think this was amazing. I guess it's a simple question. Did you just describe the fundamentals?
Yes. Yes. It might be boring for some, these fundamentals, but I love going through them. It's like reading the same book over and over again that you enjoy. You always learn something new. Even in this very presentation, I learned something. I paused for a second if you noticed. It's like, oh, I just learned something. And I'm gonna go later and contemplate on it. So yeah, fundamentals is everything for me.
So again, raise your hand up and we'll come over to you. Yeah. We do have one from the chat. So, okay, this one's about your approach to a new tech stack. Yeah. So what's the first thing you do when you begin understanding a tech stack that's new to you?
Okay, so the question is like, what is my approach when I understand new tech stack? First, if there is no desire, if there is no motivation or inspiration for me to pursue that stack, I don't even go there, right? I try never to go there because I'm forced to. And that is the most important thing, because if you're forced to do anything, then it becomes a chore, it becomes a job. You'll be boring, you'll be bored doing it. So then once I have that, the problem is solved, right? Because the rest is just me flailing and understanding things. Like, okay, what is this? And asking questions, not because the only reason I ask questions is to actually get to the bottom of that stack, right? And very few stacks interest me. Like, I rather spend a lot of time in the fundamentals. And then there's one actually that actually fascinates me. You see, there is a problem today we have, not a problem, but a limitation. We have 2 transport protocols. That's all what we have today, right? We have TCP and we have UDP. Yeah, we have QUIC, but to me, QUIC is built on top of UDP, right? We don't have a kernel level transport protocol as far as I know. That's the only two that are really 99% of the time being used, right? The problem with TCP is, the good thing about TCP is it's a streaming protocol. That means, hey, I'm just sending a bunch of bytes. That's it. Okay? And then I guarantee order and flow control and all that stuff. But that doesn't have the boundaries of messages and requests. Right? And the UDP, the other hand, doesn't have guaranteed delivery, but it has the messaging. We need both. We need something that has both. We need a message-based, reliable control that is focused on the message itself, right? And that's, I think there's one that I actually covered on my channel. It's called HOMA, H-O-M-A. And it tries to bring those two together. And that's fascinating to me.
This one over here.
Hi, Hussein.
Hi.
Yeah. So the
Hi.
W in WMEM is for write.
That is obvious, wasn't it? Thank you so much. I appreciate it.
We have another one here in the stream. What are your thoughts on KTLS, something William mentioned potentially in the future for HAProxy?
KTLS, I did not explore that. Like, that's the first time I've seen it yesterday, actually. I wanted to go back and explore that protocol a bit.
William's here, so you can talk to him after.
Yes, William, I'm going to bug you later.
Another one in the stream. What stands out about HAProxy handling requests compared to other proxy solutions?
Okay, so the reason I like HAProxy is because of the focus of all this stuff. Willie and the rest of the team focuses on these fundamentals so much, and that tweet says it all, right? Because who spend all this time and energy making sure their software runs on a 500 megahertz, with an M, guys, megahertz CPU, right? And a 64 megabyte of RAM. That's, just to have that mentality, that means your goal is efficiency. And to me, like, the most important thing is efficiency. Like, how can I be most efficient as possible? And I think that goes into our human psyche as well. Like, how can we be efficient? Because we have skills, we have talent, but what prevents us from being of maximum capacity is efficiency. We are so inefficient in most of the things we do. And that's why we have these conferences and we learn from each other to be as much as possible. Yeah, and I think that's one of the reason HAProxy try to be as much efficient as possible in everything it does.
So if people want to get in touch with you or suggest something for you to cover on your podcast or your YouTube channel, what's the best way for people to do that?
Yeah, you can reach out to me to h@husseinnasser.com. And feel free to shoot me an email.
Awesome. Well, thank you so much, Hussein. Everyone give it up for Hussein Nasser.
Thank you so much, guys.